Hey there, hackers! Sudoku is one of the most popular puzzle games. The rules are very simple. We have a grid of 9 times 9 squares, and we need to organize the numbers from 1 to 9 in a way so that each row, each column, and also each of the 9 subsquares contains only unique numbers, without repetition. We may think that a problem involving a matrix of numbers is probably the perfect case to use an array language, such as Uiua, and this is also true in some ways. With a regular mainstream language, when we work on a matrix like this, we would instantly think of writing nested for loops, or the functional geeks might resort to recursion. In Viva, however, we have no variables and rather limited forms of iteration. But we do have some powerful algorithms that would transform the only kind of data structure we have, the array. So in this video, I will present the solutions to a double challenge. First, the Sudoku validator, and then a rather difficult one, the Sudoku solver. If you follow along, you will see fun ways to work with multidimensional arrays, and you can learn some Viva techniques that are helpful to solve even the trickiest dynamic programming tasks. First, I want to point out that Sudoku may look like a numbers problem, but actually we don't need to do any math at all to solve it. Instead of numbers, we might as well use any set of symbols, colors, letters, or emoji, because the values don't matter, only their uniqueness does. I will stick with numbers, because the printed output will look better that way. Also, I will use 0 to represent the empty cell. The Sudoku board contains 81 values. In Viva, we can just take a single string of 81 characters as input and transform it to represent the puzzle, parse each value to convert the characters to numbers, then reshape to 9 columns. As for the number of rows, we can give either 9 or infinity. It makes no difference if the size of the input is the same. We can check the shape of the result. We get a two-dimensional array with 9 rows and 9 columns. The task of LeetCode Challenge 36 is to validate a partially filled Sudoku board to make sure that none of the numbers violate the rules of the game. So we need to look at a group of 9 numbers at a time, considering each row, each column, and each of the smaller 3 times 3 squares. So there are 27 total groups. If any of these groups contains a duplicate number, then the board is invalid. Looking at the rows is really trivial in Viva because our 2D matrix is already an array of 9 rows. We can just iterate through them with the rows modifier. So we want to write a validation function which takes the 9 values and determines if any of them appears more than once. And of course, we need to ignore zeros because those are still empty. I take advantage of the fact that we have numeric values here, so what we actually need to watch is the numbers greater than 0. Copy the numbers with duplicate, create a Boolean mask with greater than 0, and use the keep function to filter only the positive numbers in each group. I'm just going to box this temporarily to see what we got so far. Now there could be several other methods to do this, but we actually have a unique glyph in Viva, and this is a good opportunity to use it. How this works is that the first occurrence of any element is converted to a 1, and any other occurrences are converted to 0. So ideally, we should not get any zeros here. To find out if all the original numbers are unique, we can just multiply all of these, or alternatively, reduce minimum would also work. And we can remove the box now because each row ends up converted to a single number representing yes or no. So what we have so far is the validation of all the rows, and 1 means valid. Building the number groups from all the columns is also quite simple. We just have to transpose the array. I can keep all the rows and the columns too if I just do fork transpose ID. And because their shapes are compatible, I can simply join these two arrays to get an array of 18 rows. Now I don't even need to rewrite my validation function, it just works automatically on the whole lot. The rows and columns are validated simultaneously. Here comes the tricky part. One possible approach to create the 9 subsquares is using the window function. This is a really clever one because I can specify a multidimensional shape, in this case 3 times 3, as my window size. So let's see what happens. It does generate the subsquares for me, but actually this is way more than what I need. If I check the shape of this thing, it's an amazing 7733. Now we have entered the 4th dimension. I'm certain that Dr. Strange would give his seal of approval. Why do I have so many? The first little square is definitely the top left corner. But then the next slice is made from the 2nd, 3rd and 4th column. And I don't actually need that. From the 7 sub-rows and sub-columns, I am only interested in the first, the middle and the last one. I can use the select function to cherry-pick the indices that I want, 0, 3 and 6. This takes care of the rows of this 4D monster array. But what about the columns? I can apply the same trick on each row to filter the appropriate column indices. Now it looks better. I have a 3 times 3 matrix of 3 times 3 matrices. Finally, I will need to reshape it to 9 groups of 9 numbers. Reshaping will keep the values in the subsquares together because they have the lowest dimensionality. I can then assign this small function to a name, say squares, and join these groups with the other 18 groups that I have previously created. I just have to add some parentheses to form a function pack on the fork. And add an extra join so that all 3 arrays are combined. Again, my validation function remains the same. Now I have my 27 individual validations and all of them is supposed to be 1. So again, I can just reduce, multiply the whole thing, and even if just a single validation fails, this will make the whole board invalid. I can check with a counterexample. If I change the first value in my input, it is supposed to return false, and so it does. Wonderful, the easy part is done. Here comes the big one. In LeetCode Challenge 37, we need the program to fill all the blank cells according to the rules. I don't want to dwell too much on combinatorics, but the possible number of ways to fill the 9 digits in a Sudoku square is 9 to the power of 81, which is a mind-blowingly large number. I think you might call it a quinvigintillion. Even though I reckon only a tiny fraction of that constitutes valid Sudoku arrangements. So the point is that brute forcing our way through this problem is not feasible. In a typical programming language, we would use backtracking, dynamic programming, recursion, and similar techniques to solve this. But what can we do in a constrained array language, such as Uiua? Basically, my solution is going to emulate how a human might go about solving this puzzle. First of all, the assumption is that the initial board is valid, and at least one good solution exists. I am going to keep the possible states of the board in an array, calculating the next move one by one, until all empty spots are filled. I want to minimize the number of possible states that I am tracking. Therefore, first I will select one of the cells where the most information is available. Ideally, there could be 8 different numbers already filled across the row, the column, or inside the small square, and I only need to fill the single missing number. But there can also be more than one valid options. In that case, I will add all of them to the states array. It's also possible that a certain state becomes unsolvable. In that case, I can just discard it and pick the next one to continue from. This is how we can implement backtracking in Uiua. Technically, I think this algorithm is a directed form of DFS, or depth first search, where in each step I try to determine the shortest path to reach the target by picking the option with the smallest branching factor. That was the theory. Now let's go ahead and implement this. I can reuse the same input format and the data structure from the previous challenge. I will also store the expected solution of the test separately so that I can actually verify the result. All I need is a do loop, which will iterate until all the empties are filled. And a good approach to writing this program is breaking it down into small logical chunks that can be combined. So before I start iterating, I want to look at the exit condition. How do I know if I reached the solution? Remember that 0 means the empty cell. So my board is done when there are no more zeros. I can just de-shape the array to a single list and find the smallest value with reduce minimum. If this is 0, then I am not done yet. Otherwise, the board is filled according to the rules and the smallest number will definitely be 1. So in Uiua terms, this function is going to yield a Boolean result, true or false. Let's check the initial state and the expected outcome too. Now the next question is, how do I progress from one board state to the next one? First, I want to decide which cell to start with. Let's consider the initial board a 9 times 9 matrix of numbers. To find all the 0 values, I can simply write equals 0. This is like a Boolean mask across the whole 2D matrix. And using the where function on this gives me a list of all the xy coordinates where I still need to fill a number. At this point, there are 51 empty cells on my test data. Now I want to determine which one to pick from all these coordinates. I want to sort them based on how many different options exist for each cell. So I need a function which takes a coordinate pair and the whole board and returns all the distinct values from the specific row, column, and subsquare. This will be called taken. Comments can prove to be helpful to hint on the required arguments. Let me work on the first pair, which points to the third column of the first row on the board. And I also want to keep the board in the memory stack with duplicate. To get the row at the index of x, I extract the x value with the first function, then use the pick to index into the board. I duplicate one more time so we can compare. To get the column at the index of y, I need to transpose the board itself using the dip modifier, so this is done to the second value on the stack. Then I reverse the order of x and y, and again take the first, which is now the y value, and use pick again. This gives me the third column. To combine both operations, I can use fork just like before, and merge the results with join. At the end, I can also deduplicate to make the list cleaner. So these are all taken numbers in the specific row and column. I am still missing the values from the subsquare. I could reuse the function from the previous exercise, but I don't need all the subsquares here, only a single one. Generating them all would be a waste. I can make a slice of the board using the take function and giving a 3 by 3 array for the shape. This is almost what I need. But I may also have to shift this window by 3 or by 6 in the direction of rows or columns, according to the x and y index. Now the indices range from 0 to 8, and I can normalize this to 0, 3 or 6 with a tiny bit of math. First, divide both of the numbers by 3, then do a floor rounding. Finally, multiply them again by 3. And if you notice that division and multiplication are inverses of each other, this can be simplified to under divide floor 3. Just checking that this works well also with other possible coordinates too. For shifting the top left corner, I can use either drop or rotate. Then I take my slice of 3 by 3 and D-shape the result. Okay, brilliant. Now I can combine this with my previous forks, so now 3 operations will be done on the coordinate pair and the board simultaneously. I put it inside the function pack and join the results with the rest. And this can be placed in the taken function. So these are the numbers we cannot pick. Remember that 0 will always be one of them, because we already started out with a cell that is 0. Let's find the available numbers. First, I create a range from 0 to 9. If I just apply the member function like this, it will tell me which one of the 10 numbers are in the list that we collected. Using the not function, I just flip the ones and zeros, and again, the where function comes in handy to convert non-zero values to actual indices. I put this little one into another guess function to keep it clean. So far that looks great for a single cell. How can I apply this to all the empties? I want to iterate through all the coordinate pairs, but at the same time keep the entire board focused on each iteration. To do that, I add another dimension to the board with the fix function. Notice the small extra line in the output, and the shape now is also 199. I still need the original form of the board so I can calculate the empty coordinates. For this, the on modifier is very useful. It will apply the function but also keep the original on the top. It's a shorthand for fork identity. Now I can combine all of this and iterate with rows to see which numbers are available for every empty cell. Obviously, these lists will have different sizes, so I need to box the results. And I will even keep the coordinates on the stack rather than consuming them because I will need them for sorting. So again, I can use the on modifier just before the rows. I want to sort the coordinates by the size of the lists. I can also calculate the sizes at the same time, inserting fork length just here. And this is the point when Viva is getting a little awkward without the ability to use local variables, because we already have to juggle 3 things on the stack, and believe me, there will be more. But bear with me, we can get this done. If you have seen some of my earlier videos, you probably remember that we can use the select rise duplicate idiom to sort a list. Just to test it, I show you what it does to the length array, which is the second value on the stack. But I don't actually need to sort all the values. I just need the index of the smallest one. And that's exactly what the rise function gives me. All the indices in ascending order of the values. So the smallest length is at the index 25. I will only ever deal with the first value. Now I want to pick the coordinates and the possible moves of this index at the same time. With the over operator, which is the comma character, I copy the second value on the stack, my index, to the top. Now I have 4 things on the stack in this order: index, coordinates, index, and possible moves. Using both pick, I can index into both of the lists at the same time. And one more thing, I want to unbox the list of possible values, dipping into the second value now. I can now combine these steps to a whole function, which takes a board state and returns the coordinates and the possible values to pick next. The signature of this function is 1.2. And when actually invoking this function, I duplicate the board first, because I want to generate the possible states from it now. Bear in mind that there can be multiple moves to choose from, in case of a more complex puzzle. Just for demonstration, I add the fake value to the list of possibles. Now what comes next is that I will replace the 0 at the specific coordinate, in this case at the very center of the board, with each of the possible values. I can do this with a clever trick using the under modifier, and my values on the stack must be in a specific order for it. I need to do deep flip to put the board in the middle. There is only a single pair of coordinates and a single initial board, but I want to iterate through all the possible values. So I have to fix the coordinate array and the board as well, adding another dimension to them. Notice the vertical bars that appear in the output, showing the increase of dimensionality. And finally, the great Uiua trick to change an array under pick pop. The pick function focuses on the value at the specified coordinates. The pop removes the value and pulls in the next one from the stack. Finally, the rest of the array is restored around the value which was replaced. And we do this for each of the possible moves, iterating with the rows modifier. There we have an array which has two different versions of the board now. If I just delete the extra value that I added for testing and check the shape, it still has the extra dimension with just one board inside. This is going to be my steps function, which progresses the board to the most optimal directions based on the coordinate and the possible values. Its signature is 3.1. We are almost done here. All that's left is to repeat this process until the puzzle is solved. Remember, the strategy was to store all the potential solution paths in an array of boards and trying to progress the first one as far as possible according to DFS logic. So after formatting the input, I immediately put it in an array of boards using the fix function. This is going to be our backtracking memory and will always remain on the bottom of the stack. I need a way to pick the first board from it and leave the rest behind. I can do this with a fork, just be careful which value will be on the top. Note that I need to use the parentheses and the separator here because first and drop have different signatures, as we can see from the colors too. I can make this maybe a little bit prettier if I want to get rid of the punctuation like this. I push the number 1 on the stack, then the drop function will consume both the number and the board. The first function must ignore the number 1 and be applied only to the board, so I can add a gap modifier. There goes the next function with a signature of 1.2 that splits the board memory to first and rest. So this is what I need to repeat until the board is completely solved. I have already built that function which can validate that, so I can now create my solution loop with the do function. The condition will check the first board of the memory array, whether it's done already, and I need to use the not function because the loop must repeat as long as the puzzle is not solved. Now to neatly arrange this in a solve function, which takes the text input and returns just the single final board state. Brilliant! The solver works, at least for this particular puzzle. Let me also compare with the expected solution. I bring the solution data to the same shape using my existing Sudoku function. Then I can easily match them, and I can even view the solution next to the match result, adding the by modifier here. Great success, but we should be a little bit more careful. This particular puzzle is actually a very easy one, and there is always a move available with just a single possible option. We can even check this as a kind of debug step by printing the list of moves inside the cools function. We can observe that in each move there is always just a single value here. Now let's take a more difficult example, like the diabolical puzzle from the Sudoku Wiki website. This one also has a single solution, but requires some bifurcation and backtracking to reach it. Using the debug information, we can see that sometimes there were multiple choices and some of them ended up in an unsolvable state. Why does the program not break from this? Because we are actually just iterating an empty array and merging empty board states into our memory array in those cases. Luckily, Uiua is able to deal with this already, but if it were not the case, we could still add some error handling or branching with switch statements. One last touch is measuring how long it took the program to run. In both the easy and the difficult case, the solution is found in a fraction of a second, so we can say that it's pretty efficient. Thank you for following this far. Hopefully this video gave you some ideas how such DP problems can be tackled in the Uiua language. It was certainly very interesting and fun for me to build these solutions. I really love the fact that some tasks that usually require several loops and local variables in your average mainstream language can still be managed in a stack-based array language, even though juggling so many things on the stack can eventually get out of hand. But in my view, good commands for documentation and short, concise subfunctions can really contribute to readable code, which is not too hard to understand. If you enjoyed the show, then don't forget to press that like button, and please let me know your opinions or topic wishes in the comment section. Thank you, and see you next time.